Hi everybody. This is lecture 9. We're going to be discussing improper integrals again today. We discussed these on Monday. This is section 6.6 of the book. Friday is our quiz, our exam, which covers just chapter 6. We spent the whole semester in chapter 6, right? So this covers chapter 6. All right. Well, I want to start by reviewing what we did on Monday. So on Monday, we were talking about families of functions of the form 1 over x to the p, where p is some positive number. Some positive real number. And so we have these three families of functions. The one in the middle is when p is the number 1, we just have the graph of y equals 1 over x. When p is greater than 1, we have this blue graph which goes down faster over here and shoots up faster over here. And then when p is between 0 and 1, like 1 over the square root of x, we get a graph that does not go down as fast over here and does not go up as fast over there. So on Monday we were discussing the integrals. Now what the book calls type 1, I actually put over there, and I discuss that second. What the book calls type 2 is what I want to put first. It's an integral where your integral includes the point where the graph is discontinuous. And so you're computing an area that looks like this. Well, the deal is the green graph, even though it shoots up to infinity, does not go up very fast. And so the area is actually a number, 1 over 1 minus p, which is a positive number. But the red graph goes up fast enough that its integral diverges. And then by the comparison theorem, the blue graph is going to diverge as well. Its integral diverges. But when you integrate what I would call integrating the tail, things are reversed, sort of. The green graph doesn't go down fast enough, so it encloses an infinite area. Same thing for the red graph. It does not go down fast enough. Both of those integrals diverge. But the blue graph that goes down faster, it encloses a finite area. So on Monday I mentioned that a lot of the stuff we do this semester, I'm actually not that big a fan of, like the integration by parts, the trig integrals, all that stuff. You're probably not gonna do those integrals, by hand in your life. You're gonna use an integral tool. But it is good to know why they work, and a byproduct of studying them is you get better at a lot of things. I mean, everything is involved when we've done those integration problems so far. This stuff, section 6.6, you actually will encounter this stuff, and it really helps to have some deep understanding. Even if you use an integral tool on the web to compute values of these integrals or to find out that they don't have a value, it really helps to think about, to understand why these integrals work, and so that when you look at integrals, they start to make more sense to you. So on Monday we did those specific examples of 1 over x to the p, which is very specific, very simple. But you're going to see today that we're going to get a lot of use out of that very simple set of examples. So we're going to use them to kind of train our eyes to look at things. So example 1. Question A, will the integral from 0 to 7 of 1 over x to the p converge? B, will the integral from 13 to infinity of 1 over x to the p converge? Question C, will this integral converge? Raise your hand if you have some wisdom about these three questions. Marcy, tell us about one of them.
For A, I believe that will converge.
Anybody else want to weigh in? Yeah.
It depends on the value of P.
All right.
Yeah.
So we're integrating the discontinuity. So this is a type 2 integral. And so we don't know. So the answer is not sure. We need to know P. What about question B? Who can help me with that?
Also will converge, but you need to know P.
We don't know if it's going to converge. Right, so we're integrating the tail. Notice this is not from 1 to infinity, but the thing is we're integrating the tail. I think you get the idea. The tail is going to be in here. So we need to know P. All right, what about question C? How about some new voices here? Anybody have any wisdom about question C?
Won't it be the same rule for depending on P based on the 0 to 1 rule up there?
Well, notice I'm integrating the tail. I'm integrating the discontinuity, but I'm also integrating the tail. So go back to these. This one we're integrating the discontinuity, so we're in that left category. So it depends whether we're looking at a green or a red or a blue graph. Here we're integrating the tail. We're in a type 1 integral. So it matters whether we're looking at a green or a red or a blue graph. Now, what about this one?
It'll always diverge because it either goes to infinity for large values of P or it goes to infinity for small values of P, depending on which side you're looking at. So for low values of P, the right side will always diverge. For large values of P, the left side will always diverge.
Yeah, so basically whatever color we're looking at here, it's either going to diverge because the left side, because the discontinuity diverges, or is going to diverge because the tail diverges, or maybe both. Maybe we're looking at a red graph. So we'll always diverge. So isn't that cool? There's no more work today. We just use that, but this is a level of maturity, sort of beyond Monday, which is grinding out the numbers, which was hard in some way. But this is hard in a different way. How do we use that? Okay, example 2. So this is similar to 6.6, number 25. But you'll see that I ask a question that the book doesn't answer. And this is the kind of thing that I want you to, this is why I love studying this stuff. Consider this integral. Integral from -5 to 7, number 5 to 11 of 1 over the 4th root of x plus 5. So question A is, will this integral converge? And then B is going to be find its value. So, but who can help me with A? Will this integral converge or not? So notice a bunch of you are looking at the sideboard, which is where you should be looking. That's why that's why I asked this question, because here's where we get some mileage out of looking at this through the lens of that. Annika?
Converges.
Why?
P will be 1/4, which is the green graph on the far left of.
Right. So we are not integrating the tail. We're integrating a discontinuity here. But we are integrating at the discontinuity. This integrand is discontinuous at x equals -5. So the discontinuity is at x equals -5. And then think about what integral technique are we going to use to find this integral? We're going to do a u substitution. When we do a u substitution, we will have one over u to the 1/4. That's a green graph over there on the left category. So that's going to converge. So 1/4 is between 0 and 1, and we're not integrating the tail, we're integrating the discontinuity, so it will converge. So that kind of thinking you get much better at. You look at this kind of integral, and again, finding the value, finding out the details is going to be hard, but just knowing what you're looking for is hard in a different way. Understanding the concept of, do we expect this to converge or not? Okay, well, here we go. B, find the value. So since we know this is going to converge, I'm going to give this a symbol SA for signed area. So so we're going to do a u substitution. So I let my inner function be my u, and then I'm going to find a new version of dx. So my inner function x plus 5, that's going to be my u. So there's my green substitution. And then dx is going to be 1 over u prime du. So 1 over 1 du. So in other words, dx is just the same as du. So there's my red substitution. And then let's transform the endpoints. When x equals -5, u equals -5 plus 5, so it's going to be 0. When x equals 11, u equals 11 plus 5, so it's going to be 16. So I have now the signed area is going to be the integral from 0 to 16 of 1 over u to the 1/4 du. Now, we have to treat this as, this is an improper integral. So what this really means is the limit as a approaches 0 from the right of the integral from a to 16. And I'm going to write this as u to the minus 1/4. All right? So that's going to be the limit as a approaches 0 from the right of u to the minus 1/4 plus 1 over minus 1/4 plus 1, evaluated from a to 16. So minus 1/4 plus 1 is 3/4. So that's u to the 3/4. And then you divide by 3/4. But that's the same as multiplying by 4/3. And then you evaluate from a to 16. And then you have the limit in front of the whole thing. So this is the limit as a goes to 0 from the right of 4 times 16 to the 3/4 over 3 minus 4 times a to the 3/4 over 3. All right, so who can help me with that limit? What's the limit as a approaches 0 from the right of a to the 3/4? Just going to be 0. And what about this thing? 4 times 16 to the 3/4 over 3. What's 16 to the 3/4?
8.
8. Can you explain that?
The 16 to the 4th squared, whatever, 2 to the 3rd is 8.
Yeah, it's always good to think about ways to explain these things. So 16 to the 3/4, think of this as 16 to the 1/4 times 3. 3/4 is just 1/4 times 3, but you can let the exponents work in whatever order you want. So this is the same as 16 to the 1/4, and then that raised to the 3rd power. Well, the 4th root of 16 is 2, so we raise 2 to the 3rd power, and we get the number 8. So we get 8 for this, we get 0 for that limit, so we get 4 times 8 over 3, so we get 32 over 3. So, lots of ways you can go wrong in the calculation of the value. So it's really important to, before you embark on this calculation, think about, do I expect this to converge? If you get to the end and you think, oh, that's going to be infinity, so this is infinity. Well, no, you know that you're not expecting this to be infinity, you're expecting this to be some number. So that's very valuable. Example 2. Example 3. I changed my example numberings from last class. Example 3, consider this integral. Integral from 1 to 7 of 1 over x minus 3. A, will this converge? Who can help me out here? Got one hand up. Let's get some more hands up. Who can help me out here? Jace?
No, because it's, you have to be discontinuous in 3. And P equals 1 for that, it's infinity.
Marcy, what were you gonna?
I was gonna sorry. I was gonna say the tail, and since since P is equal to 1 in this case, that would mean that it's divergent.
We're not integrating the tail, though. We're integrating. What did you say about the tail?
The tail diverges when P is equal to 1.
But we don't have the tail here. That's the thing. We're not integrating the tail because we're not going to infinity. So we're integrating the discontinuity, and the discontinuity is in the middle of the interval, or somewhere inside the interval. So this is the first time we've done one of these in class. We'll have to do this carefully. So no tail, but the discontinuity is inside the interval. And as Jace said, after we do substitution, we'll have P equals 1. We have 1 over x, or sorry, 1 over u. So P equals 1, so it's going to diverge. All right, so question. So this one was not like a book example. That one was, but again, as I said in the book, they don't ask question A. They just say, evaluate this. But you want to train your eyes to do the faster work first. So this is not like homework, but but it's important. It's similar to a book example, but the book example I'm going to talk about in a little bit. They don't go into as much detail as we're going to go here. And because they don't go into as much detail, they don't get to a point where a lot of students will make a very common mistake. So I want to go into the weeds and do all the details and then give somebody here the chance to make the big mistake, and then we can all learn from their mistake. So B, find the value or evaluate. So we have the integral from 1 to 7 of 1 over x minus 3. Well, we have to do a u substitution. So the substitution is going to be that x minus 3 is going to be my u, and then dx is going to be the same as du, and then when x equals 1, u equals minus 2, and when x equals 7, u equals 4. So all of that goes into this substitution. So we end up with the integral from minus 2 to 4 of 1 over u. Now, this has to be broken up into 2 separate integrals. Minus 2 to 0 plus the integral from 0 to 4. Hey, let's illustrate this. Y equals 1 over u. So on the left we have that cool blue lake here. And on the right we have that lovely green hill. There we go. Now, this is an improper integral. Both of these are, so we have to do this carefully. We have to do the limit as b goes to 0 from the right of integral from -2 to b of 1 over u plus the integral, plus the limit as a goes to 0, I'm sorry, b goes to 0 from the left. Sorry, b goes to 0 from the left. And then the integral as a goes to 0 from the right, from the integral from a to 4 of 1 over u. So we can't integrate all the way to 0. We have to integrate from -2 to b and let b get closer and closer to 0 from the left. And then we can't integrate from 0 to 4. We have to integrate from a to 4 and just let a get closer and closer to 0 from the right. All right. Well, this is going to be the limit as b goes to 0 from the left of ln of absolute value of b. I'm sorry, absolute value of u evaluated from -2 to b. The integral of 1 over u is ln of absolute value of u, plus the limit as a goes to 0 from the right of ln of absolute value of u from a to 4. All right, so this is the limit as b approaches 0 from the left of ln of absolute value of b minus ln of absolute value of -2 and then over here we have plus the limit as a goes to 0 from the right of ln of absolute value of 4 minus ln of absolute value of a. Okay, so here again I'm doing more than they do in the book. In the book they just do one of these integrals, and then they say, okay, we're done. But I want to go farther. So it's helpful to have the graph of y equals ln of u and the graph of y equals ln of absolute value of u. So remember the graph of y equals ln of u is just the right side of this figure. It goes through 1, 0, goes through E1. Now what if I want to change this and make this the graph of ln of absolute value of u? What do I do? Kinsey?
Does it reflect over the
Yeah.
y-axis?
Yeah. So this is the graph of ln of absolute value of u. So I want to make sense of this expression. First of all, what's the ln of absolute value of 4? Can anybody simplify that? Yeah, this is ln of 4. What's this?
Ln of 2. Sorry.
Say again?
Ln of 2.
ln of 2. That's just a number. All right, now, we need to make sense of this. A is getting closer and closer to 0 from the right, and we're looking at ln of A. Ln of absolute value of A. So here we have A getting closer and closer to 0 from the right. And so when you come down here to the graph, ln of absolute value of A, how would you describe that y value?
Huge and negative.
Yeah, huge negative. So I've got something that's huge and negative, but then it's got a minus sign in front of it. So this thing, the whole thing, is huge and positive. So when A gets closer and closer to 0 from the right, the thing in parentheses here gets bigger and bigger positive. So what do we say the limit is? Yeah, we just say that this limit over here is infinity. Now let's go over to this side. We're looking at the left side now, the left integral. So we have B getting closer and closer to 0 from the left. So that's here. B is getting closer and closer to 0 from the left. And so how would you describe the value of ln of absolute value of B? Your hand is kind of up. How would you describe that y value? Huge and negative. Okay, so this is huge and negative. So this whole thing inside of these parentheses is huge and negative. So when B is getting closer and closer to 0 from the left, the thing inside the parentheses is getting bigger and bigger negative. So what do we say the limit is? Yeah, negative infinity plus infinity. So what's the value of the limit?
Negative diverges.
Isn't it just 0? Isn't minus infinity plus infinity 0?
No.
So you can't do arithmetic with infinity. You can't say that negative infinity plus infinity is 0. This can be confusing, but the reason it's confusing is that in your prior classes, you've probably encountered lots of situations where people will do things that look like arithmetic with the infinity symbol. And the thing is, it's not arithmetic. You're actually doing proper math with the infinity symbol that can be sort of described with a shorthand that looks like arithmetic, but it's not arithmetic. So you cannot do negative infinity plus infinity equals 0. That looks like arithmetic, but it's wrong. So this is divergent. Divergent. And so in WebAssign, if this were a WebAssign problem, you'd have to say that the integral is divergent, and then there's another box where they say give the value, and you'd have to type diverges in that box. So the value is undefined. Now you might not like that. Yeah.
Could you not break up the integral again, like from 2 to 4, and then because like it's an odd function and it's like.
Yeah, great question.
And cancel out the infinity because they would be the same.
So why can't we do this? Think about this, that bit of green area there would cancel that bit of green area, so then we're going to have some number left over. But you don't get to do that with infinity. You don't get to cancel that way. The reason is, well, there are lots of reasons why you just don't get to do that with the infinity. What that would mean would be, that would mean that every little bit of it, you're integrating in a very specific way. Like maybe integrate from here to here, and integrate from here to here, those cancel, integrate a little bit more, those cancel. But the rules for integration are not finicky like that. You don't get to do that. So you just have to say diverges, yeah. But you can see right away why you wouldn't want to be able to say negative infinity plus infinity equals 0, because clearly there's more green area than blue area. So if anything, it should be some positive number, not 0. So there are all sorts of it's like Pandora's box. If you think that you can do arithmetic with infinity, it's going to bite you. So that's where they don't go in the book. In the book, they do one of these integrals in an example, and they say, oh, infinity, so it diverges, we're done. But they don't go farther to this point where a lot of people will say, oh, the integral's 0, which is a big mistake. Okay, example 4. Which is like a homework problem, except that again, I ask a question that that WebAssign doesn't ask. Question 4 is similar to number 21. So consider the integral from minus infinity to infinity of x squared over 25 plus x to the 6th. We have 17 minutes to do this. So A, will this integral converge? Why? So, first of all, are we integrating the discontinuity? Where is the discontinuity? Marcy?
Is it at the 6th root of 25?
Well, when x is the 6th root of 25, then I get 25 plus 25, so I get 50. There is no discontinuity. The denominator is never 0. The denominator is always greater than 0. The denominator is always greater than 0. So no discontinuity. But we are definitely integrating the tail because we're going to infinity. So the question is, how is this behaving? How is the tail of this graph behaving? Anybody want to weigh in on that? You think about the tail of this graph. Well, notice that what would go in that dotted box? Starts with g and rhymes with greater than. Greater than. X to the fifth, 25 plus x to the 6th is greater than x to the 6th. Okay, so what about this? Mary, you're nodding, but nodding to what? You might just have some music playing in your head and you're just doing this. It's not, though. Jace? Less than. This number is bigger than that, so 1 over that number is less than that. So x squared over 25 plus x to the 6th is less than x squared over x to the 6th. Oh, but that's just 1 over x to the 4th. how does the integral of the tail of 1 over x to the fourth behave? Converges. Yeah. We're looking at one of these things. Doesn't matter where I start or stop the tail, you know. So, but the thing is, the integral from 1 to infinity of 1 over x to the fourth converges. So by the comparison theorem, we know that the integral from 1 to infinity of x squared over 25 plus x to the sixth also converges. And it's because of that. Because that integral converges. This is the comparison theorem, the most boring theorem there is. This graph is lower than this graph. This graph has a finite integral, so this graph is going to have a finite integral. Now, you might say, well, we're not going from 1 to infinity, we're going from minus infinity to infinity. Well, you can see the left tail, this is going to be a symmetric graph. So the left side looks just like the right side, and in the middle, there's no discontinuity. So I think at this point, we can just do the integral. But that's a cool thing. Again, notice, well, when we do the integral, you're going to see that this is not a 1 over x to the p integral at all. So find the value. So the integral, so we're going to call this signed area. It's going to be the integral from minus infinity to infinity of x squared over 25 plus x to the sixth. And so I have to break this up into two pieces. Integral from negative infinity to 0 and the integral from 0 to infinity, both times of x squared over 25 plus x to the sixth. And is everybody comfortable with the idea that this is an even function? The left side and the right side are mirror images of each other. So I can just do that integral and multiply it by 2. Also, we know that there's one integral that we've done where the denominator is 1 plus x squared. We know about that integral, but there's not a 25. And so let's get that 25 out of there. So this is 2 over 25. Let's just pull it out. And that'll leave behind a 1 plus x to the sixth over 25. So I have to correct by dividing that second term. So does everybody see that if I distribute this, I'll get 25 plus x to the sixth. I'll get back to that. Oh, but I can write this because that's a perfect square and that's a perfect square. So this is 2 over 25 times the integral from 0 to infinity of x squared over 1 plus x cubed over 5, that whole thing squared. All right, so let's do a u substitution. Oh, sorry, we've got to do a limit as b goes to infinity. Limit as b goes to infinity of 2 over 25, the integral from 0 to b of x squared over 1 plus x cubed over 5, that whole thing squared dx. Okay, so let's do a u substitution. We're going to have a green substitution to take care of our inner function. Our inner function is x cubed over 3. So that's going to be our u. X cubed over 5 is going to be our u. So there's going to be the green thing. And then we need to find a new version of our dx. So that means that, well, dx is going to be 1 over u prime du. And that's going to be 1 over 3x squared over 5 du. So that's going to be 5 over 3x squared du. So that red substitution is going to allow me to take care of that dx. So at this point, we just substitute stuff in and cancel. So we have the limit as b goes to infinity of 2 over 25. Then we have the integral from 0 to b of x squared over 1 plus u squared. And then we have 5 over 3x squared du. So then stuff magically cancels. Notice that those x squares cancel each other. And then the 5 and the 3 we can pull out front. So when I pull out the 5 and the 3, I get well, I'm just going to do this to make that. I'm afraid if I try to do arithmetic in my head, I'll crash and burn. Okay, so the 5 over 25 gets together and has a party. That becomes a 1 over 5. So this is 2 over 15 times the limit as, this should be 0. The limit as b goes to infinity of the integral from 0 to b of 1 over 1 plus u squared. All right, so who remembers what the integral of 1 over 1 plus u squared is? Marcy's got a hand up. I want to get like 5 hands in the air. Liam. Yeah, wonderful. So this is 2 over 15, the limit as b goes to infinity of arctan b minus arctan 0. Now what's arctan of 0? In other words, what's the angle whose tangent is 0? Hanukkah?
0?
Yeah, so let's just review things. So here's the graph of y equals tangent of x. The key thing is it has vertical asymptotes at x equals pi over 2 and x equals minus pi over 2, and it goes through 0, 0. So to do y equals arctan x, I interchange all the x and y coordinates. So this is y equals arctan x. First thing you do is you transform the asymptotes. Instead of x equals plus and minus pi over 2, we have asymptotes at y equals plus and minus pi over 2. And then the graph goes through 0, 0 and does this. So there we go. There's the graph of arctan x. You can see that arctan 0 is 0, and that's because tangent of 0 equals 0. Now we're asking this. On this graph, if I go way out to the right, b is going to infinity. What are the values of arctan b getting closer and closer to? Mark, let's get some new hands up. Cassidy, your hand was up to take a drink of that soda. Can you tell me what is this getting closer and closer to? Yeah, exactly. This is getting closer and closer to pi over 2. This is just 0. So this is 2 over 15 times pi over 2. So that's pi over 15, which is really pretty. It's gorgeous. You got to admit, that's a really pretty thing. So we're looking at this integral. Gabriel, get a good shot of me with this graph. This is a great graph. All right, so so you can see how much work this was. You know, how many chances there are to make a mistake here. So it's really cool to know at the beginning that we're going to expect this to be a number. And again, that kind of thinking, you get really fast at this. You get a bit faster at this, but you get really fast at this, and it trains your eyes so that when you look at something like this, you think, well, okay, this is not an integral of 1 over x to the p. It ends up being, you know, something related to arctan. But knowledge about how this compares to one of those 1 over x to the p graphs gets us a lot of wisdom. All right, great. Thank you, everybody. Thanks, Gabriel, for recording. I'll hand back quizzes.